Functions let us write much bigger and more complex programs than would otherwise be possible. And the power of functions is even greater when integrated with a deliberate approach to software design. In this lecture, we'll see that functions integrate really well with top-down design approaches, and functions integrate equally well with a bottom-up approach to design. This is where we work up the hierarchy, using individual functions as building blocks. We'll start off by combining two concepts for managing complexity that we've already encountered separately: top-down design and writing our own functions. And we'll do so from the perspective of designing a game. With top-down design, we take a larger problem and we treat it as a set of smaller problems without worrying as much about how each of the smaller problems impact the other smaller problems. Our job with any one task is to either break it into even simpler subtasks or implement it directly. With functions, we have a very similar motivation. A function is a way of conceptually separating one set of functionality from everything outside. And this is very similar to the way that we treat each of the subtasks in top-down design. So, if we consider the tree structure that we create in top-down design, each of the nodes can become, in effect, a function of its own. Instead of merely turning the hierarchical tree into a series of comments, we can turn it into a collection of functions. Now remember that since we must have a function declaration before we call the function, this means that the functions listed earlier in the code will be those from far from the root of the tree. The main function will correspond to the root of the tree and come last. Let's see what this might look like by designing a program to play a game of Connect 4. The game of Connect 4 is played by two players, each with a different color piece, usually red or black. Players take turns dropping their piece down columns of the board. When a piece is dropped, it travels as far down as it can until it's either at the bottom or on top of another piece. And the goal is to get 4 pieces in a row, vertically, horizontally, or diagonally. Now let's think about how we would create a simple version of this game, first by generating a top-down design. To get started, we can say that there are 3 main problems our program needs to solve. First, we need to set up the board. Then, we need to repeatedly take turns. And finally, we need to determine and display the winner, or note that it's a tie. Next, we can break those problems into smaller tasks. So initializing the game will involve getting the board size for the game, then initializing that board to be empty. Traditional Connect 4 is played on a board with 7 columns and 6 rows, but basically any size board could be used. We can get the board size from the user. For each turn, we have a few things that we need to do. We want to display the current board for the players. We want to get the player's next move. Then we want to make that move, and then check to see if someone won. And these steps will happen repeatedly through the game. And finally, for declaring the winner, we want to print out the board one more time, and then print out who the winner is. Now, while most of those elements are now about as simple as they can be, checking for a winner can be broken down further. We'll need to check for various win conditions: a vertical win, where someone has 4 consecutive pieces in the same column, or a horizontal win, where someone has 4 consecutive pieces in the same row, and an increasing or decreasing diagonal, where a player has 4 consecutive pieces in an increasing or decreasing diagonal. And if none of those are the case, then we should check to see if the board is full, in which case it's a tie game. Now, notice that the process for checking for a winner is basically the same as the process for printing a winner. We have to make all the same checks in both cases. This is one of the places where we can take advantage of the fact that functions allow us to use the same code for multiple calls. We can write one set of functions that should be able to be used in both of these other functions. We also have a display board node in 2 different places, both as something that we do at the beginning of each turn, and as something that we do before printing the winner. And again, we can write one function that gets called from 2 different locations, thus saving us coding time. So, we've broken down the game into a series of subtasks, each of which can be implemented in a function. And we've even identified a way to reuse some of our functions. Next, we're going to turn each of those nodes from our top-down design into a function in code, with main as the root node. There are 22 nodes, but some of those are repeated in multiple places. So overall, there will be 15 functions in addition to the main function. At the beginning, we'll just create these functions, not worrying initially about the return types or the parameters for each. We'll come back to adjust that as we fill in the functions. For instance, we can create functions for the first branch of the top-down hierarchy. We'll have one function to initialize the game. Under that are two more functions, one to get the board size and one to initialize the board. Since the function to initialize the game is higher in the hierarchy and will need to call the other two functions, it should come last. We can do the same for all the branches right from the start, or we can begin filling in these functions. Just to make the illustration easier, I'll go ahead and fill in the code for these functions to see how it works. Let's take the first function, getBoardSize. Basically, we need to ask the user what size board to use, and then return that size. Now the size will actually be two numbers, a number of rows and a number of columns. So, since we need to return two values, we'll use a pass-by-reference approach. The code for the function itself is very straightforward. We just output a couple of prompts, and we read in the number of columns and rows to use. And these will get returned to the calling program using pass-by-reference. Now, remember that when we write a section of code, we should test it and make sure it's stable before going on. When we finish a function, we want to run what are called unit tests on it, testing that it works as it's supposed to. So, we'll just set up a call to the function in the main program and output what it returns. And we do this and see that it's all working. And although we should perform tests like this for every single time we write a new section of code, we're not going to do so in this case just for the sake of time. You'll notice in the code that we just saw that not all of the functions we intended to write had code. In this approach, building a function that doesn't actually do anything is somewhat common when developing programs. You might know that a program will need this function, and you might need to call the function from the code you're working on, but you haven't actually written that other function yet. When we have a function that can be called and returns some value of the correct type, we call that function a stub. Stub functions are useful as a way to develop one piece of code at a time, to use the incremental development approach that we should be using. Now, sometimes the stub function will just do a tiny bit of computation to provide some result that's at least valid, beyond just being the right type. But the key is that we aren't trying to write that entire function at the same time. Now likewise, we sometimes need some other data or operations to be performed before we call a function, but we don't necessarily want to write all the code needed before that function that we're working on is called. So in this case, we write what's called a scaffold. A scaffold gets things set up so that a function we care about can be called and tested. For example, if we have a function that's supposed to analyze a vector of numbers in some way, we'll need some code to produce a vector of numbers that we can pass into the function. And this code to set up the environment, to create the vectors just to test the function, is a scaffold. So, we can continue to fill in additional functions now. For instance, we can fill in the initializeBoard function. It'll need to take in the number of rows and columns, and it will return a board. In this case, our board is going to be a vector of vectors. There will be one vector for each column, and thus a vector of each of those. Each element of the board will be a 0 to indicate that the spot is empty. Now, notice that the initializeGame function just calls the two other functions that we created. It calls getBoardSize to get the number of rows and columns, and then initializeBoard to actually create the empty board. If we'd wanted to do this in a different order, that is, to write the initializeGame function first, then we'd have had to have made stub functions for the getBoardSize and initializeBoard functions. And going on from there, we can fill in all the other functions corresponding to each node in the hierarchy that we created in our top-down design. We'd want to develop incrementally to add one function's code and test it thoroughly before we go on to write the next function. Now, this entire program is a little too long to go through item by item. It's about 200 lines long. The thing to realize, though, is that the 200 lines are spread over a bunch of different functions. No single function is too large, and each one should be understandable on its own. In fact, let's look at the function with the most lines of code, 19 in total. That's our display board function. This is a function to print the board to the screen. The function itself, even if it's a few lines long, should be simple enough to understand. Take a look at it and see if you understand it. The function is going to loop over all of the rows and all of the columns. For each position, it'll output either a period, if the position is empty, a 1 if player 1 has a piece there, or a 2 if player 2 has a piece there. And there's a new line printed at the end of each row. You might notice that the board is stored as a vector of columns, where each column is a vector of the positions from the top row to the bottom. Now we could have stored the board a different way, but this happens to be convenient for Connect 4, where people place pieces by column. In any case, the point is that the functionality here, in one of the leaf nodes from the top-down hierarchy, is pretty easy to understand. Assuming that you knew how the board itself was stored as a vector of vectors of ints, you could have written this yourself. And you don't need to know much else about the program in order to write this function. You don't need to know whose turn it is, or if someone's winning, or anything else. The display board function is one of the leaf nodes. So let's look at one of the interior nodes also. We'll look at the take turn function. Taking a turn consists of 4 steps. First, we display the board, then we get the player's move, then we update the board based on that move, and finally we check to see if the game is over, if someone has won, or if the board is full and no more operation is possible. If the game is over, we return true, otherwise we return false. As we look at the code, we see that each of those operations is just made up of one function call to another function that we've already defined. We call display board, then get move, then place piece, and finally check winner. Because of our top-down design, it's easy to understand this function and what it's doing. The details of each of those functions are pushed off into those function definitions rather than putting the details here. So let me encourage you to spend some time looking at this code and seeing how it reflects the top-down design of the program that I outlined earlier. Top-down design combines very easily with function definitions to make what would otherwise be a challenging problem much more tractable. So, we've seen that functions integrate well with top-down design. But top-down is not the only way to design, and in fact functions make it easier to use an alternative approach called bottom-up design. The idea of bottom-up design is to take existing things that you know how to do and combine them to do something new. And then you could use that to do something else, and so on. Let's take a simple example that we might use in a word processor. Say that you have a function pause first that lets you find the first occurrence of some word in a string. And say you have another function, replace string, that lets you replace one section of a string with a different string. We can look at those and imagine, hey, we can easily use these to replace the first occurrence of one word with another word. So we'll create a new function, search and replace, that will replace one string with another inside of that larger string. Now, how might you write that function? That is, how would you fill in the code for search and replace based on what we have here? Notice that I'm not even showing the details of how those other functions are implemented. You can just assume that they work. Here's how it might be implemented. We can use the pause first function to find the first position of the string that we're searching for. And if it's not found, we return false. Otherwise, we identify where that string would end in the original string. And finally, we call replace string to replace the string and then return true. And you can build up from there to create another level. We can combine the function that we just had with a loop. And that will let us replace every occurrence of one word in a string with a different one. We can create a new function, building up from the function that we just created, that just repeatedly loops over the previously defined function until it returns false. That is, until it can't find the string to search for in the longer string. Again, we've used some simpler functionality to build up to a more complex functionality. Bottom-up design like this is a great way to add features to a piece of software. When you have a product that can already do one thing, and then you have some new idea that integrates well with it, you can then end up creating a new software product that incorporates an additional feature. Bottom-up designs tend to focus on what's possible with what I have, rather than the top-down philosophy of how is this particular problem solved. As a result, bottom-up implementations tend to be useful in a wider range of applications. And this makes bottom-up a good way of developing a library of related functions, a bunch of functions that you might use across a range of domains. So, I want to talk a little bit about what it means to build a library. Now, if you're going to have a library, you're going to want a namespace to help you separate the functions in your library from others. We've seen namespaces before. They're the name and the double colon that you have to put in front of certain commands. And you should be very familiar with the using namespace standard that we've been putting at the beginning of every program, enabling us to use commands in the standard namespace without writing std::: in front of everything. When we talked about namespaces previously, it was already in the context of functions loaded in from specific libraries. If you remember, namespaces are a way of helping us distinguish one library's functions from another's. And that way, if one library has a function named getData, then another library can also have a function named getData. They can be in different namespaces, and the two functions can remain distinct. Well, we can also create our own namespaces. To do this, we just write the keyword namespace, and then the name that we want to use for our namespace, and then in curly braces we include all the function declarations that will be part of that namespace. Let's see a simple example. If we want a namespace named English, we simply write namespace English curly brace. Inside the curly braces, we have a function that is type void named greeting. And all that function does is print to the console, hello. This function greeting is being defined as part of the English namespace. In the main function, we can call this function by writing English: greeting parentheses. And that means that we're calling the function named greeting within the English namespace. So when that call is made, hello is printed out. Okay, now suppose we create two namespaces, one named English and the other named Spanish. Each of these can have a function inside named greeting, but the one in Spanish says hola instead of hello. If there were not different namespaces, we'd receive an error for trying to redefine a function. Now, we can call each of these separately, writing English: greeting parentheses, and then Spanish: greeting parentheses, to call the two different functions. And sure enough, when we run this, we get two different outputs, both hello and then hola. Notice that if we leave off the namespace from the function call, then we can't get anything. There's no plain function named greeting available, only the function greeting in a particular namespace. Now, notice that we could add in a using namespace English line to our code. And just like when we have using namespace standard, this means that if there's a function call that's unresolved, then we use the one in the English namespace. So, when we run this code, now we get the output, hello. Now, note that we had to put using namespace English after the namespace itself was defined. If we'd put it in at the top of the program, well, there was no English namespace at that point, so the compiler would give us an error. If we were to change our command to using namespace Spanish, then we would have seen hola output. Remember that having the line using is generally discouraged, and this is because when you look at a line of code, like the call to greeting in the code that we just saw, we don't automatically know from that one line which particular greeting is being called. Now, this is a place where we have a trade-off between convenience and clarity. It's much more convenient to just write using namespace English one time, rather than having to type English : before every function call. But you're less likely to have a mistake if you always use the namespace explicitly. The reason that all of this is useful is for the development of our own libraries of functions. And just like we have libraries such as IOStream that provide us useful functions, we can create our own libraries to use in a similar way. So to do this, we want to put all of the new functions that we create in a separate namespace to prevent any possible collision in the naming of different functions. Now, when we have separate libraries, and as we start wanting to write really big programs, the types that are built by teams of people or by one person working for a really long time, we can begin to make use of another feature, which is called separate compilation. Here's the rough idea of how this works, and I'll illustrate it with a really simple program. Say that we want to create a library of functions. The common practice in C and C++ is to break the code for these functions into two separate files, a header file and a source file. Header files usually have a .h or sometimes a .hpp file extension, while source files will have a .cpp extension. Now the header file will contain the namespace, any variables to be defined in that library or namespace, and the function declarations. The function declarations are just the header part of the function, not including the curly braces. The declaration is a way of saying there will be a function with this signature, but not actually saying how that function is implemented. The actual implementation is called the definition. And up until this point, we've been putting the definition with the declaration. And that's commonly done when everything's in one file. But the header-like declaration and the body-like definition can actually be split up. So in this example, we've got a file greeter.h, and it declares the namespace with the line namespace, my namespace, curly braces. Inside of the curly braces, it will have the function declaration. The function will be named greeting, it'll have a void return type, and take no parameters. Now, since the function definition will be in a different file, we need to put the word extern in front of the declaration. The word extern just says that, yes, we know that we need a function definition, and it'll be in the separate source file. So, our only real line, other than the namespace, is just extern void greeting parentheses semicolon. Notice that we had no definition, no curly braces for the greeting function, and we ended with a semicolon. Now in the other file, the source file, we'll have the definitions for any functions that weren't defined in the header file. The source file must pound include the header file. So we would have greeter.cpp containing the definition for the function named greeter. We start by pound including greeter.h, the file that we just defined. That is, we're going to use that declaration here. We also pound include IOStream, and we write using namespace standard since we'll be generating console output. We then have our function definition. Now notice that we've put the namespace in front of the function name to make it clear which function we're defining. So we have void my namespace, : greeting, parentheses. And then in the curly braces, we have a single cout statement to print howdy. Now, we write the code that we want to call the functions in our library in a different source file, a different .cpp file. That file needs to pound include the header file. And this is what we've been doing when we pound include header files for libraries like IOStream. So in our example, we have £1 include for the greeter.h header file that we defined before. That is, we're going to import the my namespace and the function that's declared there. Then we have just a single function call to my namespace : greeting. When the compiler runs, it will compile each of the source files separately. In each case, there's machine code generated. For the library source file, there's no main function, so there's nothing to execute. There's just a compiled version of each of the functions. For the main source file, it has function calls that are from the library, but it doesn't actually have the definitions of those functions. It just knows the signature. So, after the machine code is produced, there's a linker stage that matches up the function calls from the new source file with the implementation that's in the library. And when these are linked up, the result is an executable that can be run. Now, if you want to try this out, you'll probably need to use an IDE like Visual Studio rather than an online browser-based compiler. The browser-based compiler usually won't let you create multiple files, so there's no way to have multiple source and header files. In your IDE, let's look at how to create your separate source and header files. In Visual Studio, the separate files that you create are not automatically put into your project, so you will have to add the files to the project when you're ready to compile them. To add the files to the project, after saving them, you go to the project window, then you select Add and Existing Item, and you'll then add all three files to the project: the source file that contains main, the header file, greeter.h, that contains the function header, and the source file, greeter.cpp, that contains the function definition. Then you can build the project or run it. Xcode automates putting the files in the project. Your project starts with the main.cpp file that should contain main, automatically appearing. And then you can just go to the File menu, create a header file, saving it as greeter.h, and then a source file, saving it as greeter.cpp. If you create the .cpp source file first, Xcode will give you the option of also creating the header file automatically. Now when you create these, they're automatically in the project, so you can just build and run the program. The source files will be compiled separately, and then the linker will link them together. And when we run the program, we indeed get howdy printed out. When designing your program using pseudocode to lay out your functions, take a look at all of them and look for places where you might want to reuse the code. Or a file might seem to have too many ideas in one place, like if we wanted to split the game process for checking for a winner out from the process of making a move. Those are good times to consider breaking functions into separate files. There are a lot of reasons why separate compilation is useful, particularly for larger programming tasks. It makes it easier to reuse files in other programs. You write the code once, and then you just include it in other programs. Dividing functions across files helps ensure that no single file is too large, and that everything in one file is closely related. And by separately compiling files, only the files that change are ever recompiled. On large projects, that can greatly improve productivity. In fact, we could separately compile every function we write: game.h for a header file, game.cpp for source files, and so on. However, for beginners, I think it makes code a little harder to follow, and you wouldn't be able to execute such code from a browser-based development environment. My rule of thumb is to consider separate compilation when you might want to reuse code or to simplify your files. The main thing to take from this lecture is that functions let us develop much bigger software programs more easily. They fit into the top-down design approach, and they make it feasible to implement different pieces independently. They support bottom-up design, and they can be pulled out into separate files that act like libraries that we can import into our programs. And all of this lets us deal with programs at a scale that's just not feasible if we tried to put everything into one long set of commands. Starting in the next lecture, we're going to be exploring an entire style of programming developed around objects and classes. And this will bring us into the heart of the features that set C++ apart from C. We're going to start learning object-oriented programming.